What's up, guys? In previous lecture, we talked about the difference between atomic mass and atomic weight. Let's review whatever we talked so far. Okay, so just tell me, what is atomic number? Atomic number is what? Is the number of protons, right? P plus, right? And what is the mass number? Mass number is the combination of proton number as well as what? The combination of the neutron, right? So the proton and the neutron are going to give you the mass number. What about atomic mass? Atomic mass is nearly equal to what? Mass number, and it is like slightly different depending on the binding energy, but we're not going to talk about that. Just we're going to consider this as like same as the mass number. Atomic weight is the average AVG of what? Naturally occurring what? Naturally occurring isotopes of what? Of same element. Okay, for example, carbon 12, right, and carbon 13. If you just like average them, the atomic weight, right, average them, that you're going to get atomic weight for that particular carbon, which you're going to see in the periodic table, right? The periodic table is the atomic weight, which is the average of naturally occurring isotopes. So what we're going to talk today though, okay, what's going to be the focus in today's lecture? So we're going to talk about these two guys. If you know them, just tell me what's the name. All right, the first guy, his name is what? His name is Rutherford. His name is Rutherford, Rutherford, Rutherford. And the second guy, his name is Planck, Planck, Planck. And these people have a great role. They played a great role for creating or to give an idea about how the atomic structure is like we perceive, right? Nowadays we know like how atoms look like, and these people actually did experiment and give more and more idea about atomic structure and more than that. Okay, so let's talk about Rutherford. What he did was he found that, okay, if some atom is there, in the center or somewhere there is a very dense positively charged stuff there. He did not know that it was nucleus, but he found out like by doing this experiment, as you can see here. So what he did was he actually bombarded these alpha particles, right, through this gold foil, as you can see here, right? This is a gold foil, and this gold foil basically here, right? And what he did was some of the rays, these alpha particles, right, these rays were deflected, as you can see, right, these scattered particles, right? And because this positive particle, because the alphas are what? These alphas are helium 2 plus particles, right? When they go, because these are positive, that's why they got deflected, right? That's what we saw there. And he found out that one. Okay, he did not know what it was, but he just said there is something like densely positively charged stuff there in the atom. And the guy here down here, the Planck, he is known for what we called is the quantum theory. He actually developed the first quantum theory. And we're going to talk about him more when we're going to talk about another guy whose name is Bohr in future lecture. For now, what you need to know is what he did was, okay, if there is a matter, let's say, if this is a matter here, right? This is a matter. Now this matter, right, think about like this way. So, the energy that is emitted is, electromagnetic radiation from this matter, right, is actually in the form of like small, let's say, pocket, let's say these small quantities, okay, and the energies are like in a discrete bundles, right? And he called them quanta. Okay, and this quanta has that energy. Okay, and the energy is emitted in the electromagnetic radiation. What do you call that? Electromagnetic radiation. Now again, remember that he give the relation. Okay, he give the relation. The relation looks like this. Okay, as you can see here, the relation looks like this. So the energy E equals hf according to him. And some people write this F like the Greek letter V. Okay, it doesn't matter unless you know it. Okay, then E equals hf, where E is the energy, right? E is the energy. H is called Planck constant. This is a Planck constant, whose value is also essential to know. Okay, so you have to know this: 6.626 times 10 the power negative 34. What is the unit? Joule times second. Okay, F is the frequency, right? The hertz, the unit is hertz, right? And now we can just manipulate this equation by like doing this: equals h c over lambda. Why? Because we know this F, the frequency, is basically a c over lambda, where c is what? Speed of light, which is what? 3 times 10 to the power 8 meter per second. Now we can see that the energy and the wavelength has inverse relationship. What does that mean? When the energy is more, then the wavelength is low, right? But what about the energy and the frequency? When the energy is high, the frequency is high too, which you can see from this here, right? The energy and the frequency relation here. So this is one of the useful equation he gave us, and we call this as a Planck relation. And the Bohr, another guy we're going to talk in future, right, in other lecture, he actually used his idea to actually came up within his Bohr model, and he explained how it works in greater detail, which we will focus in next lecture.